Everybody, I'm CJS24, and this is my presentation on the flow across flying discs. For my experiment, I took 3 different disc shapes, and the goal is to compare how the 3 discs fly to one another, and then determine what throwing velocities might be the best for each disc. The 3 disc models utilized were the Frisbee, the Fault disc, and the Frisbee ring. These were then meshed and put into the fluid setup. Due to the fact that these discs will encounter low velocity streams, it's appropriate to use the incompressible Navier-Stokes equations, which can be seen here. In order to determine the turbulence that impacts the discs, the K epsilon turbulence model was chosen. The equations utilized by Fluid for that can be seen here. The simple scheme was the solution method utilized to obtain the results. The momentum equations were discretized spatially using a second-order upward method. This produced a solution that was accurate to the second degree with respect to both x and y. And due to the nature of this problem, the solution was obtained iteratively, and therefore it is stable. Here's the overall problem layout. Here at the front, we have the inlet with the air streams coming in to flow across the body. Here at the back, we have the outlet. Surrounding the disc, we have the free-flowing air, and then here in the center, we have the disc, which was modeled by a solid body that has a no-slip condition along its surface. Next, we move on to the results. First, we have the results that are obtained for the Frisbee. Here, we can see the streamlines moving over the body in a very smooth fashion. Next, we have velocity versus lift and drag. It can be seen from this graph that the values of drag are actually greater than the values of lift at each of the velocities. Here, these upper 2 images represent the pressure distribution across the disc. It can be seen that along the upper surface, an area of low pressure forms denoted by these cool colors. And then on the bottom side of the surface, a thick high pressure layer forms. These bottom 2 images represent the turbulence encountered by the Frisbee. Figure 4 here shows that the highest turbulence values are encountered along the lowest trailing edge. Next, we have the results for the Fault disc. Here we see the streamlines moving very smoothly once again. The streamlines show an increase in velocity as they go over the disc, which is denoted by the change in color from yellow to orange. Here we can see the lift and drag for the Fault disc. It can be seen that the Fault disc had higher values for lift at each of the velocities, and that the lift over drag ratio actually increased as velocity increased. Here we see that areas of low pressure form near the upper surface of the Fault disc, and beneath the Fault disc, a thick layer of high pressure forms. Figures 7 and 8 show that the Fault disc encounters higher values of turbulence than the Frisbee did. Similarly to the Frisbee, the areas of highest turbulence occurred along the lowest trailing edge. Finally, we have the results for the Frisbee ring. Here we see the streamlines moving across the extremely thin Frisbee ring. It can be seen from the change in color that the streamlines which go underneath the Frisbee ring are showing a decrease in streamline velocity. Here we can see that the values of lift produced by the Frisbee ring were very constant across the velocities, and they were actually negative values. The drag values, however, actually increased as the velocity increased, but it should be noted that these drag values are still significantly lower than the drag produced by the previous 2 discs. Here we see the pressure distribution. It is nearly symmetrical from the top to the bottom of the Frisbee ring. It can be seen that near the Frisbee surface, we have the lowest pressure, and then as we radiate outwards, pressure increases. This lower figure here, figure 10, shows that the turbulent kinetic energy is the greatest about midway across the Frisbee ring body. All this leads to a few conclusions. The standard Frisbee, which produced the highest drag values across the board, is the best for low throwing velocities. This is because as the velocity increased, the ratio of drag over lift also increased, and therefore the drag was beginning to dominate as velocities got high, and therefore is the best for low throwing velocities. The Fault disc, which was the only disc that produced values of lift higher than the values of drag at each velocity, would be the best for high throwing velocities. It was observed that the ratio of lift over drag increased as velocity increased, and therefore the fault disk is the best for high throwing velocities. The frisbee ring would produce nearly negligible values for drag, would be the best used in a wind environment. Not only does it produce very low values of drag, but due to the fact that there's a large cutout of material in the center of the disc, it would not be impacted as greatly by the forces of the wind. So those are my conclusions. Thanks a lot for listening.